If I were to ask you what science fiction and upper limb prosthetics have in common, you'd probably say something like sleek and sexy artificial hands. But you'd be wrong. What they really share in common is the paradox. In science fiction, it's usually a time travel paradox. In prosthetics, it's a technology paradox. Engineers keep making better materials, better computers, better manufacturing processes, and better sensors, yet the most common prosthesis used in 2018 is still the body-powered hook, which was developed in 1912. And while the hook has certainly been greatly improved since then, the artificial hands of Luke and Anakin Skywalker, unfortunately, still remain works of fiction. Now, these paradoxes in science fiction are almost always resolved, but here in science fact, the resolution remains illusory. And the real reason for this is that most people with upper limb amputations have only lost one hand, so they still have one fully functional hand. And what this means is unless your device is as good or better than their existing hand, they're just going to learn to do things one-handed. That any small inconvenience, such as your device being heavy, hard to use, or fragile, are going to cause them to abandon it. And this is why of the 20 to 30,000 people in the US with upper limb amputations, only about 56% use a prosthesis. Now, all of these state-of-the-art prosthetic hands are electrically powered and use high-precision electric motors, transmissions, and mechanical linkages. And while these are really cool, they all have a fundamental issue, and that's that they're trying to replicate the human hand, something that's conformable, robust, and highly versatile, with something that's heavy and fragile and rigid. My solution is to use an artificial muscle fiber to replace these electric motors. To do that, I use a material called a liquid crystal elastomer, which is a material that can contract when exposed to ultraviolet light. Now, I can control the material properties to develop something that's as strong as natural muscle. However, the stronger you make this material, the less it's going to contract. So to get around that, I can make these into fibers and then twist these fibers into coils, like a spring. And these coils can contract up to 26% more than the straight fibers. The end result is something that's small, lightweight, strong, and flexible, and that contracts in response to ultraviolet light. Now, by using fiber optic cables to provide that light, I can create extremely small and robust actuators that are much better at mimicking natural muscle than electric motors. And using these in prosthetic hands will make them lightweight, more robust, and more flexible. Now, just as resolving a paradox in time has lasting consequences for the future, so too does resolving this paradox of technology. By changing the fundamental actuation technology in prosthetic hands, we open the door to creating the perfect replicas of the human hand that we've all come to expect from science fiction.